So we're now going to talk about convolutional neural networks, which is one particular type of neural networks that works best with imaging inputs when we are expecting an image as an input. So CNNs or convolutional neural networks are widely used today in every field, in every aspect of our lives, really. So it is mainly used in social media, right? Vastly used, and it is used in e-commerce. It is used for facial recognition, especially for law enforcement purposes. So I put a video about this in the supplementary material on Canvas if you would like to see some information about facial recognition. It is used in text to audio or audio processing in general. It is used for self-driving cars in healthcare. Convolutional neural networks are really a success, and they've achieved fascinating, impressive performance results when it comes to any type of imaging inputs, really. So convolutional neural networks, or CNNs, have gained a lot of success in computer vision, especially in object recognition. So if we discuss the concept of recognizing objects, for us as humans, how do we know the difference between an orange ball and the fruit, the orange fruit? So if we think about it, how did we learn the difference? So in our brain, in our mind, there are differences in terms of textures, right? There are differences in terms of some things that exist in one but not in the other, like the leaf. There are differences probably slightly in color and other things. So these things, we call them features. So this is the main idea with CNNs. They're trying to extract some useful, smart features, interesting features in the imaging inputs to enable us to learn and recognize objects or other patterns in the image. Okay, so to us, when we see this input picture, what we see is a smiley face, right? But to the machine, it doesn't really see it that way. To the machine, what it sees is just a grid of pixel values. Okay, so in this case, if it was just a binary image, meaning just black and white, it only sees a grid of ones and zeros, right? That's what the machine sees. In the case of color imaging, then what the computer sees is again a grid of pixel values that range from 0 to 255. And then if the image is binary, which is just black and white, it only sees a 2D input, versus if it's a color image, then it sees a 3D input that has 3 channels, right? Red, green, and blue. So another challenge that we should mention is the MNIST challenge. So it's a task to recognize handwritten digits. So the inputs were images of handwritten images. So they don't really actually look like that. So the actual data set was white paper with hand written digits in black. Okay, so this one was inverted actually. So the data sets consisted of 60,000 images for training and 10,000 images for testing, and all the contestants should train their models on this training data, and when they evaluate their model and they had a satisfying result on the validation set that they can create out of this, then they go ahead and test it on the 10,000 testing instances and report results. So this so this table shows the evolution of the testing error again over the years using multiple different classifier types. So you can see here linear a linear classifier which achieved a 12% accuracy. You can see k-nearest neighbor. We haven't talked about this one yet, but we will do next week. You can see that the error dropped from 12 to 4% when we started using just a two-layer neural network. And then from there, support vector machine achieved an error of 1.4. We will talk about SVMs again next week. And then from there, convolutional neural networks, namely LeNet5, was able to achieve a 0.95% accuracy. And then people have tried all different types of convolutional neural networks with all different variations and depths. But today the error is at 0.01%. Can you imagine that we can recognize handwritten digit images using convolutional neural networks with 99.9% accuracy? So this is what a CNN really looks like. So starting with an input layer and again an output layer, just like we've seen so far. The difference here, the input will be actually an image, right? Remember, CNNs work best with imaging inputs. And then the output can actually be the class. If we're trying to do classification, then given this image, the output can be the class car. So the CNN predicts that it recognizes a car in the image. Now the structure of a CNN is really just like we said about multi-layer perceptrons. So you can have multiple hidden layers between the input and the output layer. The only difference is that these hidden layers are of different types. They're not like we've seen with multi-layer perceptron, which is just a set of neurons that are connected with each other fully. So this type of interconnection, we call it fully connected layer. And this is one type of the layers that CNN has. However, CNN has other special type of layers, namely convolutional layers and pooling layers. So the convolutional layer are specific types of layers that apply convolution operation to the input images. So the convolution operation main objective is to extract useful features from those inputs, okay? And so it is quite similar to what we did before with multi-layer perceptron, which is the weighted sum of the input times weight plus bias, right? So this is quite similar, but at a different level. So here the input has 3 channels. So mainly it's color images that are that have R, G, and B channels. And then for each channel, what you do is you choose a filter, which is for us, we've called it a weights, right? It is still called weight, but the dimension is different here. So we can choose a window of weights. In this example, it is a 3x3 window. And this 3x3 window is called a filter. So we slide this window over our input image, right, left to right, top to bottom. We're scanning our input image to extract useful patterns and useful features. And so while we're scanning that sliding window, what we do is just the multiplication of the weight times the input, which is the pixel value, and then we add the bias, and this will give us the output at the other side. So that's what the convolution operation in simple words. When it comes to the pooling layer, the pooling operation is a dimensionality reduction operation. So we're trying to reduce the size of our inputs while we are moving forward in our in different layers. So the idea, if we are using something called max pooling, for instance, so again, we're going to choose a slide-in window. In this example, it's a 3x3. So when I look at the brown area here in the input, I will pick the maximum pixel value. So if we look at the very first 3x3 area, the maximum pixel value will be 3. So I pick 3 and I put it in the output side. Again, I will slide my window to the next one, right, which will be this one, and then the maximum pixel value in that window is again 3. So I put 3 in the output side, and so on. Okay, we can have a variation of the max pooling. Instead of max, we can have average pooling. Okay, this is a very common one. The same idea. So we calculate the average out of all the pixel values in our slide-in window. So you can see that as an input, we started with a 5x5 size, and once we did the pooling, we ended up with a 3x3 output. So the main objective is to reduce the dimensionality. Right, so if we are using max pooling, then we're going to choose the maximum out of each window. So in the first window, the maximum value is 20, right? The maximum here is 30, the maximum here is 37, and the maximum pixel value here is 112. Whereas if we were using average pooling, we're going to calculate the average of these 4 values, which is 13. The average of these 4 values, 8. The average of these values is 20, and so on. Okay. So given the starting input and then the set of the convolution and pooling operations that we do multiple times in different layers repeatedly, so you can have 2 convolution layers, 300,000, depends on your application and the size of your data set. Then you finish up with the fully connected layer, which is the normal layer where all the nodes and neurons are fully connected to each other. And then you end up with an output layer where the model is basically outputs a probability for the input to belong to each one of your classes. So in the case of the MNIST, which is the handwritten digits recognition problem, we have 9 classes, so the digits are 0 to 9, and then the model will give you the probability that this input belongs to class 0, it's 0 probability. The probability that it belongs to class 2 is 0.1. The probability that it belongs to class 5 is 0.1. The probability that it belongs to class 7 is 0.8. And we pick the maximum probability, and therefore the predicted class will be class 7. And indeed, you can see that this input image has 7 digits in it. The digit 7 in it. And so this shows the different popular CNN architectures. So there was AlexNet in 2012 with the ImageNet challenge, and from there VGG16, then ResNet 50, and then lately in 2020 EfficientNet was really the big thing. And then from there, starting from 2021 probably, transformers started to take over, especially vision transformers for imaging inputs. So sometimes, we said deep learning models need big data to train, okay? So if you don't have big data, if you don't have thousands to millions instances, then do not even think about using a deep learning model. Now, if you have, let's say, a few thousands and you want to somehow upgrade and augment your data, we can use some data augmentation operations, which are represented in a set of transformation operation that we apply to our input data. So starting with this cute little kitten, we can apply some zoom in or zoom out. We can do some rotation left to right, just slight degrees that won't change the meaning of the input. So even if you rotate to left or right, you can still see a cute little kitten. So this doesn't change the meaning. When you zoom in or out, you can still recognize a kitten. So things like that, small transformations to your input data that will make the size of your input data set bigger, but in reality, you're just transforming the original set. So if you start with just one image, you ended up multiplying that with 6 using data augmentation operations.